Good afternoon, everybody. Today is the beginning of Unit 1, Day 1, and we're going to begin with talking about exponents. Specifically, we're going to talk about zero exponents and negative exponents. Now, these are some of the harder concepts to get our heads around, so what I'd like to do is spend some time looking at what an exponent is, just so we're very, very clear on what the expectations are and what we're talking about. When we have a whole number, or what we call a base, and we take it to an exponent, and an exponent has a couple different names. Sometimes we call it a power, or sometimes we call it an exponent. Here we're calling them an exponent. What that really means is you're going to take the base number this many times, and you're going to multiply it together. So that is all an exponent means. And now, typically with numbers that are easy, like 2s and 3s and 5s and so on, we're going to go ahead and multiply this out. 2 times 2 is 4, times 2 is 8, 8 times 2 is 16. So 2 to the 4th power equals 16. And that's all there is to working with exponents. The exponents are usually going to be whole numbers, but they can be negative, they can be decimals, they can be fractions, they can be a variety of things, but when we're just beginning with them, we'll typically stick with whole numbers for now. The exponents are always going to be positive in any simplified expression. So anytime you're looking at an expression that you need to simplify, only positive exponents may be used. If you have negative exponents, or if you have a zero exponent, you have to do something else to them. So one more time, this is key for you. Only positive exponents may be used to simplify expressions. Now, in thinking about different expressions, we could surely come up with different examples, but they would just be multiplication problems over and over again. And since perhaps it'd be nice to have a shorter video this time, let me go ahead and begin by exploring simply some patterns with you. Now, when I think about patterns, I'm going to stick with an easy number like 5 to the 3rd power. And when I think about 5 to the 3rd power, I think the base written 3 times, so 5 times 5 times 5, multiplied together gives me 125. So 5 to the 3rd power equals 125. If I go down one level and I have 1 less 5, 5 to the 2nd power written twice is 25. Okay, I can handle that. Now 5 to the 1st power is the base written one time only, which is 5, which brings me to what happens when this number turns to 0. Now, when I end up with ultimately a 5 to the 0, the question is what is going to happen? And let me show you what happens and why. We have this special rule that says 5 to the 0 power equals 1. And the way in which to describe this is if I were to take 125 and divide it by 5, I get 25. Excuse me. If I take 25 and divide it by 5, I get 5. So following that same pattern, if I take 5 and divide it by 5, I get 1. Okay, so that's how the pattern works. So then what happens when we go one step beyond? 3, 2, 1, 0. You can probably guess the next number in line here will be -1. So what happens when you have a negative exponent? Well, imagine we go ahead and take the number 1 and we divide it by 5 again. No, we're not going to do long division. We're going to go ahead and use fractions. So if I take 1 and divide it by 5, I get the fraction 1/5. That's 1 divided by 5. That's it. If I go again, I'm going to divide that by 5 again. 1/5 divided in 5 equal pieces is 1/25. Now, I can write it a variety of different ways. I can write it as 1 over 5 times 5, 1 over 25, which is the most common, or 1 over 5 squared. And this is interesting because this looks a lot like this one, with some slightly different formatting. In fact, there's some similarities, 5 to the -1 and 1 over 5 to the +1. And if we go one more layer down, we have 5 to the -3rd, and you might see again some similarities. 1 over 5 times 5 times 5, that's what happens when you keep dividing by 5. That is 1 over 125, or, this is neat, 5 to the -3rd, and 1 over 5 to the +3rd are exactly the same thing. That makes me think that when I see something with the negative exponent, since my rule was to simplify expressions, only positive exponents may be used, this is most definitely not a positive exponent. It makes me think that I could rewrite the problem like this and have a positive exponent, and then this would be simplified. Now, there will be some time to talk in class about whether we would prefer 1 over 5 to the 3rd or we would prefer 1 over 125. They are equal after all, so in fact, it really doesn't matter. It just depends on really what your teacher's asking for or what program you're using and what the request is. But this is a really easy result. What will be interesting is if it continues and happens a second time. So let's look at a different series of bases with some similar exponents. Here is 3 to the third power, a base of 3 and an exponent of 3. So 3 written 3 times, which is 27. 3 to the second power is 9. 3 to the first power is 3. And once again, if we imagine the rule, this time we're dividing by 3, that's the base. And we divide by 3 again, that's the base. Well, I could guess that 3 divided by 3 is 1. So I predict I'm going to get a 1, and there it is. And if I go one more time, divide by 3, I'm going to get a fraction 1/3. And there it is. It's a little sloppily written, but there it is. And if I go one more, divide by 3, I'm going to get 1/9. And there it is again. Now, once again, while 1/9 is a really common way to write the problem, I do want you to note how interesting this is, that I can rewrite a problem with a negative exponent like this so that I simplify the expression, as only positive exponents may be used. So anytime I see a negative exponent, I feel like I can rewrite it in this same format with a positive exponent. And that would probably lead to a rule of some sort, and possibly the end of this video. So let's see how we do here. There are 2 rules that I want you to take away from today's video and a few examples, and we're all done. First, anything that we're going to be using, and for anything I'm referring to this variable x, anything to the 0 power, now not including the number 0 itself, but any non-zero value taken to the 0 power equals 1. So if I have 8 to the 0, it equals 1. 7 to the 0 equals 1. 5 to the 0 equals 1. 4 to the 0 equals 1. A variable a to the 0 equals 1. Everything to the 0 power for our purposes right now equals 1 because we followed those patterns. And we're kind of simplifying or formalizing this rule that we thought we observed. Anything with a negative exponent can be rewritten as a fraction with 1 over the same exact piece, a to the n, but without the variable being negative. Sorry, without the exponent being negative. So notice how this relationship exists. Now what I'd like to do is I'd like to finish the video with some examples, and then you can use not only the rules, but the examples to answer the questions that are in your notes and get more math and on the exit ticket. So we're going to begin with the example on the left, 6 to the 0. Well, that's easy. Something to the 0 equals 1, so that's a 1. 8 to the negative 1, that looks like this rule. So if this is 8, that shows up on the bottom, so 1 over 8. And if I have a negative exponent, it shows up as a positive exponent, but in the bottom. So negative 1 becomes a positive 1 on the bottom, and I have 1 over 8. Now, I'm not going to write the 1 here. The truth is it's the same either way, but this is a much neater, cleaner way to write your answer. So we'll leave it as 1 over 8, and we just understand that there's a 1 there as an exponent. Let's not get bogged down. Let's keep going. 4 to the negative second looks like this rule. So 4 to the negative second becomes 1 over 4 to the positive second. Sometimes this is acceptable. Sometimes 4 times 4 equals 16, and this is acceptable. These are both good examples of answers. One with a positive exponent and one that's been fully simplified. 100 to the 0. Well, that's here. Anything to the 0 is 1, so that's easy. You might like those. Those are nice. The middle column here has some variable pieces. Let's not let that throw us off. X to the negative fifth, that's just like this. So instead of the a to the negative n, we have x to the negative fifth. So it's 1 over x to the positive fifth. The goal here is to write them with a positive exponent. And since I don't know what x is, I can't do anything more with it, so I'm done. Next piece down, a to the 0 looks a lot like this one. Let's keep going into the third column. Now, the third column poses some unique challenges. They're beyond the basics for sure, but definitely something that can be a little more challenging to many. Let's start with this one. I noticed that this one has a negative exponent, but the negative exponent is in the denominator. So now I'm going to ask you to take a look at the rule and look at this. Every time we see some value with a negative exponent, we turn it into a fraction where the denominator becomes positive. What if the denominator itself was negative? I feel like just like this flips kind of and goes down to the bottom and becomes positive, we're going to go ahead and flip this back to the top and make it positive. Now you could say 4 to the third over 1 and put it on the top. That's okay, but nobody really needs divided by 1. So we would say 4 to the third, which is a perfectly acceptable way, or 4 times 4 times 4 is 64, so that would be an okay answer as well. But this is an interesting move, right? If it's negative, it comes down. If it's already down, it goes back up. Either way, it switches from negative to positive. Let's see another application of this. Here we have two bases, a to the third, and on the bottom, b to the negative second. Now the a to the third doesn't really follow either one of these rules, so we're not really going to do anything with it. We're literally just going to make our fraction and keep a to the third on the top and just leave it alone. The b to the negative second, however, is kind of like 4 to the negative third. It needs to come up to the top. So if it comes up to the top, I'm going to put b, and it becomes positive, b to the positive second on the top, and now we're done. There's my answer. If you wanted the over 1, you could use it, but we don't need that as we showed in the previous example. And one more down here before I flip the paper and we call this video done. Here I have 3 different things going on. I have the 6, which doesn't really go along with either one of these, so we're just going to write a 6. We have an a to the negative second. Notice how it's not in a fraction, a lot like the rule, but we have to turn it into a fraction. So what I'm going to actually do is I'm going to rewrite this problem, and I'm going to make a fraction and put a to the positive 2 on the bottom. That means this thing went down. And then the final piece, b to the fourth, just like the 6, the b to the fourth, just like the a to the third before it, doesn't have anything going on in these two rules, so it just stays where it was before, right next to the b, and now we have ourselves a simplified expression. This is a little more complex. What I'd want you to take away from this one is that we have a 6 and a b to the fourth, both of them having positive exponents. We don't move those. Notice they stay the same. The negative exponent has to get moved. Only the negative exponent moves. Now, as we finish this video out, I have 3 more examples, and then we'll be done. First, if I have a fraction with an exponent, and it's a whole number exponent, or a positive exponent, here's what I do. I'm going to go ahead and say that I could take the 1 on the numerator to the second power, and I can take my denominator, 3, to the second power, and then we evaluate this expression. 1 times 1 is 1, 3 times 3 is 9, and I'm all done. Let's look at the second one. This case, same as the one before it. I'm going to take the numerator, it's a whole number, so 2 to the third power, and 3 to the third power. And now I'm going to multiply these out in my head. 2 times 2 times 2. 2 times 2 is 4, times 2 is 8. And 3 times 3 times 3, we did that one earlier, is 27. So my answer is 8 over 27. Sorry for the sloppiness. Last one. Let's not change the rules at all. Watch what we do. We're going to get, just like we did here with our exponents, going to the numerator and the denominator, we're going to get 4 to the negative second and 5 to the negative second. And then we're going to apply the rule that says if we have something negative, it has to switch. But look at this. They both have negatives, so they both switch. So we get 5 to the positive 2 and 4 to the positive 2. And since 5 times 5 is 25 and 4 times 4 is 16, our answer is 25/16. Now there's a lot to take in this video, but the goal was to keep things short and simple. So good luck with Unit 1, Day 1 on 0 and negative exponents.